Hello everyone, myself Dr. Dhruv Kumar, Assistant Professor of Chemistry, Guru Nanak College, Budlada. Today we are going to discuss about alkyl halides or haloalkanes. So, what is an alkyl halide or haloalkanes? An organic compound at least one carbon halogen bond, one CX bond. X may be fluoride, chloride, bromide or iodide, which replaces H from the hydrocarbon. It may contain one or more than one carbon halogen bond. Properties of some alkyl halides or haloalkanes: they act as fire resistant solvent, refrigerants, pharmaceutical and precursor of many organic syntheses. These are examples: methyl chloride, ethyl chloride, propyl chloride. One hydrogen atom is replaced here by halogen atom. The nature of carbon halogen bond. As we know, halogens are the most polar substances in periodic table. So due to the more electronegativity than carbon, so carbon halogen bond is polarized, and carbon has partial positive charge and halogen has partial negative charge. Due to the electronegativity difference, we can represent it like this way. As we know, the electronegativity decreases in the order of fluoride, then chloride, bromide and iodide. This Due to this, carbon halogen bond length increases. Fluoride, chloride, bromide, iodide. Carbon iodide bond length is maximum while carbon fluoride bond is minimum. If we talk about the dipole moment, the order is carbon chloride 1.56, carbon fluoride 1.51 and carbon bromide 1.48 and carbon iodide, that is minimum, 1.29. Typically, the chemistry of alkyl halide is denominated by this effect and usually result the CX bond breaking either in substitution reaction or elimination process. This reactivity makes alkyl halide very useful reagent for organic synthesis. Now, naming of haloalkanes or alkyl halides. Again, here we are choosing the longest chain of carbon. If contain double or triple bond is present, we are giving the numbering so that the substitution get the minimum number. Like here we are 5 bromo 2,4 dimethyl heptane. We are starting numbering from this side and second carbon get the first substitution, then 4, then 5. The naming we do alphabetical order, like bromine come first, so we write here bromine as compared to dimethyl. Okay. Again 2 bromo 4 5 dimethyl heptane. If more than one or same kind of halogen atom is present, so we use word di, tri or tetra. If there are several different halogen atom present number, then we do alphabetical order, like 2 bromo 5 methyl hexane. Bromine come first from the methyl, so we write the name 2 bromo 5 methyl hexane, not 5 bromo 2 methyl. Okay, because bromine come first, so start numbering from this side. If we will do numbering from this side, it will get second position. Again bromine is second position, but alphabetically bromine is first, so we will do numbering from this side. Again 2,3 dichloro dihalogen compounds, we use word di or tri. Dichloro 4 methyl hexane. Primary, secondary and tertiary alkyl halide compounds. It depends on primary, like here carbon is primary carbon, carbon is secondary carbon, and carbon is tertiary carbon. According to this, we give the name primary or 1 degree halogenoalkane, secondary or 2 degree halogenoalkane, tertiary or 3 degree halogenoalkanes. Physical properties of alkyl halides or haloalkanes. All organic halides are insoluble in water and soluble in common organic solvents. Boiling point increases with increasing in molecular weights. Therefore, the boiling point increases. Order is fluoride, then chloride, then bromide, then iodide. 1 chloropropane, molecular weight 78.5, boiling point 47. 1 bromopropane, molecular weight 125 and boiling point is 71. So this order is following here. Boiling point also increases for straight chain isomers like 1 bromobutane, boiling point 101, 2 bromobutane, there is a branching 91, 2 bromo, 2 methyl propane, again there is more branching, boiling point is 73. Preparation method of alkyl halides. There are various methods for preparing alkyl halide: direct halogenation of alkane, addition of halogen halides to alkenes and alkynes, action of hydrogen halides on alcohol, action of phosphorus halide on alcohol, action of thionyl chloride on alcohol, halogen exchange, and Hunsdiekar reactions. We will do one by one. First, halogenation of alkane. It involves the substitution of hydrogen atom of alkanes by many halogens like chlorine, bromine, iodine or by fluorine. Generally we will avoid fluorination because reaction takes place explosively. So we need very milder condition, but other we can do it, like methane reacts with chlorine in the presence of UV light or at high temperature 300 degree, yield methyl chloride or chloromethane. Methane, chlorine molecule, UV light or temperature 300 degree, we will get methyl chloride and HCl. Now addition of hydrogen halide. Alkenes have carbon-carbon double bond, reacts with hydrogen halide like HCl, HBr or HI to form alkyl halides, ethyl bromide, like this. If we have 2 butene, then we get 2 bromobutane. So this is the another method of generating alkyl halides. Action of halogen acids on alcohol. Alcohol reacts with HBr or HI to produce alkyl bromides or alkyl halides. Ethyl alcohol reacts with HBr, give ethyl bromide. If we will talk about mechanism, we know HBr, H positive and Br negative we get. Further, this Br negative attack this carbon, alpha carbon next to OH, and this OH will react H positive and H2O will formate and ethyl bromide is formed. Action of phosphorus halide on alcohol. Alcohol reacts with phosphorus halide to produce alkyl halides. Ethyl alcohol PCl5. We get ethyl chloride HCl and POCl3. Mechanism, here is mistake. Ethyl chloride is here. Mechanism: ethyl alcohol. This is the structure of phosphorus pentachloride. This Cl and this H will remove from here and we get this anion, and this oxygen lone pair is attached to the phosphorus positive, and again Cl is removed from here and it will go to this carbocation and we will get ethyl chloride and POCl3. Action of thionyl chloride on alcohol. Alcohol reacts with thionyl chloride in the presence of pyridine to produce alkyl halide. Ethyl alcohol reacts with SOCl2 and give ethyl chloride plus SO2 and HCl. As mechanism is concerned, this H and this Cl is removed as a HCl, and we will get this anion. This lone pair attack to the S positive, and this Cl remove its bond pair and attach to this carbocation, and we will get ethyl chloride and acetone. Halogen exchange reaction. This is another method. Alkyl bromide is heated with concentrated solution of sodium iodide NaI in acetone, the presence of pyridine, to form alkyl iodide. Ethyl bromide and NaBr is removed from here, and ethyl iodide is formed. Hunsdiekar reaction. Silver salt of carboxylic acid react with halogen to give unstable intermediate, which is further decarboxylated to form alkyl halide. This is silver acetate, reacts with Br2, we are getting CH3COOBr, and then Br radical is removed from here, and this radical is formed. Again this CH3CO bond is break, and CO2 is formed, and methyl radical and Br radical then combined and give methyl bromide. This reaction is known as Hunsdiekar reaction. Radical mechanism is taking place here. Now the reactions of alkyl halides. Alkyl halides give nucleophilic substitution reaction like substitution of I hydroxyl group, substitution by amino group, substitution by alkynyl group, substitution by alkoxy group, substitution by thiol group, substitution by thioether group, substitution by an ester, substitution by cyano or isocyano group, reduction of alkyl halides, elimination reactions, Wurtz reaction, and reaction with metals. We will do one by one. First, nucleophilic substitution reaction. Nucleophile, we know, any reagent that donates an unshared pair of electrons to form a covalent bond known as nucleophile. Nucleophilic substitution reaction in which one nucleophile is substituted for another. There are two types of nucleophilic substitution reaction: SN1 unimolecular nucleophilic substitution and SN2 bimolecular nucleophilic substitution. This is nucleophile alkyl halide. This nucleophile attack here, and this X is removed from here, and we are getting this substitution product. First, substitution by hydroxyl group. Alkyl halides react with aqueous potassium hydroxide to form alcohol. Ethyl bromide react with NaOH, and NaBr is formed, and ethanol is formed in the presence of water. SN1 or unimolecular nucleophilic substitution. In this reaction, bond breaking between carbon and leaving group is completed before bond formation with nucleophile. This type of reaction is classified as unimolecular because only alkyl halide is involved in rate determining step. Okay, rate is determined or depend only on alkyl halide. So what happened? Methanol, it will give the nucleophile CH3O negative and 2-methyl propane. After the reaction we get 2-methoxy, 2-methyl propane, and HBr. As far as mechanism of SN1 is concerned, first, ionization of CX bond gives 3-degree carbocation intermediate. Tertiary butyl bromide, this bond will break carbon bromide, and it is slow, and this step is rate determining step. This is the tertiary butyl carbocation is formed and bromide radical. Now in next step, nucleophile will attack here, and oxonium ion is formed. It is planar, so any side of attack can be take place, and then Br, this H will remove from here as HBr, and we are getting 2-methoxy, 2-methyl propane. So this is the rate determining step, slow step, and Further, the attach of another nucleophile attack is the fastest step. If we talk about the energy profile diagram of SN1 reaction, there are two peaks, this and this. This is the rate determining transition state peak, and this is the final product formation peak. And this tip is the formation of carbocation intermediate. Between these two peaks, this is the stable intermediate, and the final product has the lower energy. SN2 or bimolecular nucleophilic substitution. It is a concerted process. Bond breaking and bond formation take place simultaneously. This types of reaction is classified as bimolecular because the alkyl halide and nucleophile are involved in rate determining steps. So rate will be K alkyl halide as well as nucleophile. NaOH, methyl bromide, nucleophilic substitution, we will get methanol and NaBr. Mechanism. Nucleophile attacks the reactive center from the opposite side. This nucleophile will attack this carbon from the opposite side, and from the other side Br is leaving. And this is the transition state form. There is a partial bond formation and partial bond breaking is taking place, and ultimately we get the product and NaBr. Energy profile diagram of SN2 reaction. Only one rate determining step because one transition state is formed here. Initially reaction is slow, and after transition state reaction will faster. First, this is the energy of activation, transition state is formed, and then product is formed very fast, and we get the alcohol as well as NaBr. Now SN1 versus SN2. SN1 is a unimolecular, SN2 is bimolecular. SN1 most favorable alkyl halide, tertiary, secondary and primary we know because tertiary halide will give stable carbocation 3 degree and secondary will give the 2 degree carbocation. So these are the favorable condition. 3 degrees most favorable. While alkyl halide in SN2 reaction 1 degree is favorable because backside attack is taking place here, and 2 degree will rate slow. Why? Because there will be crowding. 3 degree there will be more crowding, more steric hindrance, so reaction rate will be slow. Nucleophile will attack slower as compared to primary alkyl halide. Reacting nucleophile is weak in case of SN1. In case of SN2, reacting nucleophile is strong base. In SN1, solvent is protic, like alcohol. In SN2, generally we use aprotic solvent like DMSO, dimethyl sulfoxide, acetone, etc. In SN1 reaction, stereochemistry is mixed retention as well as inversion. Because carbocation is formed planar intermediate, both side attack can be possible here. But in SN2, stereochemistry is inversion taking place. Factors that affect the SN1 and SN2 reaction. SN1 good leaving group, alcohol, better leaving group, faster the reaction. Reactivity order 3 degree, 2 degree, 1 degree. Here the reactivity order in SN2 reactions. Stable carbocation is formed. Here transition state is formed. Weaker base or alcohol, water. SN2 reaction favor strong base. Polar protic solvent, polar aprotic solvent. Only substrate concentration faster the reaction. Here concentration of substrate as well as base both faster the reaction strong. First order kinetic, it is the second order kinetics. And reactivity order is 1 degree fast, there is mistake, then 2 degree, then 3 degree, okay, as we discussed earlier. Now substitution by amino groups. Alkyl halide reacts with alcoholic solution of ammonia to form amine. Okay, ethyl bromide reacts with ammonia in ethanol, give ethylamine. Mechanism: NH2 nucleophile is formed here. This nucleophile attack to this carbon because we know this is partial polarized. Carbon has partial positive charge, or after breaking carbon bromide bond, carbocation is formed. So this nucleophile attack here and we get ethylamine and HBr. Substitution by alkynyl group. Alkyl halides react with sodium acetylides to form higher alkenes. Mechanism: this bond is break, this carbon ion is generated here, and further this carbon ion attack to this carbon and this Br is removed from here and but1 ion is formed. Substitution by alkoxy group. Alkyl halides react with sodium methoxide to form ethers. Sodium alkoxide is prepared by dissolving sodium in alcohol. This method of making alcohol is called Williamson ether synthesis. That is very important method for synthesis of ether. So ethyl bromide react with sodium methoxide give methoxyethane. CH3O Na bond is break. CH3O negative nucleophile is formed here and Na positive. This nucleophile attack to this carbon and this Br will remove from here and we are getting the corresponding ether. This is the unsymmetrical ether. Substitution by thiol group. Alkyl halide react with potassium hydrosulfide to form thiols. KHH, SH negative and K positive will form here. Further this nucleophile will attack this carbon and ultimately we get the thioalcohol and Ki. Reaction with potassium sulfide. Alkyl halide reacts with potassium sulfide to form dialkyl sulfide. K2S reacts with ethyl iodide 2 moles and it will give diethyl sulfide. Mechanism: this bond will break from here 2 molecule Ki and this simultaneously bond will form here diethyl sulfide. Reaction with silver salt of carboxylic acid. Alkyl halide react with silver salt of carboxylic acid to form ester. Ethyl bromide react with silver acetate in the presence of ethanol, give ethyl acetate and AgBr. Mechanism: the silver acetate will ionize CH3CO negative acetate ion as well as Ag positive. This acetate ion will attack to this carbon and Br removed from here and ethyl acetate is formed and AgBr. Reaction with sodium cyanide to form alkyl cyanide. NaCN we use Cn negative. This nucleophile attack to this carbon and iodide removed from here and it will combine to Na positive NaI and ethyl cyanide is formed. Reduction of alkyl halides. Alkyl halide undergoes reduction with nascent hydrogen in presence of reducing agent like zinc HCl to form alkanes. Alkyl halide H2 zinc HCl alkane is formed methyl iodide. If we use then we get the methane. So it's the method of synthesizing alkanes. Elimination reaction or dehydrohalogenation of alkyl halide is the another important types of reaction. When alkyl halide is heated with alcoholic solution of sodium hydroxide to form alkene and hydrogen halide. NaOH in alcohol heated alkyl halide and this halogen and hydrogen dehydrohalogenation is taking place here and corresponding alkene is formed. If we use propyl chloride in the presence of NaOH heating we get the propene. Further the generation of alkene will depend on the stability. It will discuss we further later in elimination. Another important reaction is Wood's reaction. Higher alkanes are produced by heating alkyl halide with sodium metal in dry ether. Two molecules of alkyl halide lose their halogen atom, add NaX, and that result to joining of two alkyl group to yield symmetrical alkane having even number of carbon atom. Alkyl halide we are using two molecule here and we are using 2Na dry ether condition. Symmetrical alkane is formed plus 2NaX. If we use methyl halide, we are getting ethane and NaBr. Reaction with metal, formation of Grignard reagent. As we know, Grignard reagent is the most important or very much important reagent in organic chemistry. So alkyl magnesium halide or you can say Grignard reagent are also obtained by treating alkyl halide with magnesium in anhydrous ether to give alkane. Alkyl halide, magnesium, dry ether, driest condition we get alkyl magnesium halide. This alkyl magnesium halide when treated with water, alkane is formed and magnesium halide hydroxide is formed. For example, if we are using methyl magnesium iodide and water, we get methane and MgIOX. Now some uses of alkyl halides. Ethyl chloride used to prevent pain caused by injection or you can say muscle pain, injury pain. Chloroform, solvent for fats, wax and rubber, preparation of chloropicrin or chloritone. Trichloroethylene to remove grease from metal parts used as a solvent. Tetrachloroethylene same removing grease from metal parts used as a solvent for dry cleaning. Dichloromethane strong solvent, flammability, vapor pressure, depressant, viscosity, thinner it is used. Tetrachloromethane, propellants for aerosol, dry cleaning, degreasing, fire extinguisher, pesticides. These are the use of tetrachloromethane. Hydroform, it's used as a disinfectant and antiseptic. In summary, alkyl halides are organic compound containing carbon halogen bond. The polarizability of carbon halogen bond greatly influence the chemical reactivity of alkyl halides. So it's go various types of reaction and very useful reagent for organic synthesis. Alkyl halide undergo nucleophilic substitution reaction SN1 or SN2 mechanism. Both depend on the reaction condition. Alkyl halides also form important Grignard reagent, which is very important reagent for organic synthesis. These are the references. Thank you very much.